we're going to continue to look at worked examples involving aqueous equilibria. Okay, the first one we'll look at today is one involving a KSP expression, and this is one that involves writing the equilibrium constant expression for the solubility product of silver chromate. When silver chromate dissolves, it will form 2 silver ions and 1 chromate ion. Okay, as shown here, 2Ag plus, and chromate has a -2 charge. The exponents in the expression will correspond to the stoichiometric coefficients. So silver ion will be squared, chromate will be to the first power. All right, the next question involves a particular saturated solution of silver chromate and has a silver ion concentration of 5 × 10⁻⁵ and a chromate concentration of 4.4 × 10⁻⁴. What is a KSP? Okay, well, we wrote the KSP expression in the previous problem, and so we'll substitute these values in here. Don't forget to square the silver term, and we get 1.1 × 10⁻12. Okay, so that tells us that this is not very soluble. All right, the next question says a saturated solution of silver chromate prepared by dissolving solid silver chromate in water has a chromate concentration of 6.5 × 10⁻⁵ molar. Okay, so calculate the KSP for silver chromate. Okay, because both silver ions and chromate ions come from the dissolution of silver chromate, silver must be twice as much as chromate. Okay, so substituting the silver and the chromate values into the equilibrium equation will give us the value of KSP. Okay, and again, don't forget to square the silver ion concentration. Okay, so we get the same number as we did in the last problem. Okay, so here we have calculating solubility from KSP. Okay, so first we need to write the balanced equation for the solubility equilibrium. That would be magnesium fluoride solid dissolves to form Mg2 plus 2F minus. And at equilibrium we have X for magnesium and we have 2X for fluoride. All right, the second part of the problem, grams per liter. Second part of the problem, grams per liter, simply involves using the molar mass, 62.3 grams per mole. Right, so the molar solubility, we would find X using this method. Magnesium is X, fluoride is 2X. We would also square the 2, so combining terms, this comes out to 4x cubed. Divide both sides by 4 and then take the cube root. So the molar solubility is 2.6 times 10⁻⁴. Okay, and then the solubility in grams per liter, we would just use this factor, 62.3 grams per mole. Okay, moles divide out, and we get 1.6 times 10⁻² grams per liter. Okay, let's look at a solution that contains a common ion. Okay, so calculate the molar solubility of magnesium fluoride in a 0.1 molar sodium fluoride solution at 25 degrees. Okay, unlike the previous problem where fluoride was just 2x, this is going to be 0.1 plus 2x. Okay, the 0.1 is from the added sodium fluoride. Okay, so we substitute x into our equation. We substitute 0.1 plus 2x, and we need to square this term. Okay, but it turns out that we can approximate. We can assume that 2x is much smaller than 0.1. Okay, if we compare 0.1, which is 10 to the minus 1, with 10 to the minus 11th, okay, this is going to be much larger, and the 2x should be negligible. Okay, so this makes our calculation a lot easier. Okay, so we square 0.1, and that gives us 0.01, and we divide both sides by that. And that gives us 7.4 times 10 to the minus 9th. Okay, so having that extra sodium fluoride in there reduces the solubility by a factor of about 35,000. Okay, so here we have a calculation involving the concentrations of complex ions. The question is, what are the concentrations of silver, the silver amine ion, the silver diamine ion, in a solution prepared by adding 0.1 mole of silver nitrate to 1 liter of 3 molar ammonia. Okay, so we can see that we have a very large excess of ammonia. Okay, and then the Kf values, this should actually say 10 to the 7th, 1.7 times 10 to the 7th. This is 2.1 times 10 to the 3rd, and then 8.1 times 10 to the 3rd. Okay, so this is the overall process. Silver complexes with 2 ammonia molecules to form the diamine silver ion. And since this is a large number, we make the initial assumption that 100% of the silver is converted to the silver diamine complex. And then there's a tiny amount of back dissociation that takes place. Okay, so we start out, we say that silver has 0. Okay, we've gone all the way to product. And since all of our silver was used up, that tells us that initially our silver diamine complex is 0.1. Okay, where we get that, we start off with 0.1 molar, and so all of this is used up. This is a 1-to-1 ratio, so that's where we get the 0.1. The ammonia concentration initially, okay, we start off with 3 molar ammonia, and this is a 2-to-1 ratio. Okay, since there was 0.1 of this to begin with, it reacted with 0.2 of the ammonia, and so that leaves 2.8. All right, so these are the amounts that we start off with, and then after 100% reaction, we assume that all of the silver has gone to the complex, so there's 0. 2.8, this is from the previous slide, and then 0.1. Okay, and then doing the back dissociation, this would decrease by X, silver would increase by X, and then this would increase by 2X. Okay, so this is the, okay, so here's the K1. I'm sorry, this is a KF. So we substitute these values from our table, and we can assume that the X in the numerator and the 2X in the denominator are both negligible. And if we solve for X, we get 7.5 times 10 to the minus 10th. Okay, so yes, indeed, these terms are both insignificant compared to 0.1 and 2.8. So that would be our silver concentration at equilibrium. Okay, the silver diamine complex would be 0.1 minus X. And again, we solve for X up here. 0.1 minus 10 to the minus 7.5 times 10 to the minus 10th is still about 0.1. And then we can calculate the concentration of the intermediate from the K1 value as shown here. Okay, so the comment here is that nearly all of the silver is in the form of the diamine silver complex. Okay, and that's clear from the values that we got for our calculation. Okay, here we have an example of exploring the effect of complex formation on solubility. Okay, so we'll calculate the molar solubility of silver chloride at 25 degrees in pure water and in 3 molar ammonia. Okay, so we start out by writing the balance equation for the dissociation reaction, and we define X as the moles per liter of silver chloride that dissolves. Okay, so we've got two processes. We got silver chloride dissolving, and we need to know the KSP, so this is the value of the KSP. It's a 1-to-1 ratio, so each one of these is X, so the molar solubility is would be the square root of this, and so that's 1.3 times 10 to the minus 5th. Okay. Okay, silver chloride plus 2 ammonias produces the silver ammonium complex plus the chloride. Okay, and the way they got this equilibrium constant was to take the product of the two equilibrium constants, the KF and the KSP. Okay, so if we add the KSP process with the complexation of the silver ion actually cancels out, and then this is the result. Okay, so we'll define X as the number of moles per liter of silver chloride that dissolves. And then a saturated solution contains X moles per liter of the diamine silver complex, X moles per liter of chloride, and 3 minus 2X moles per liter of ammonia. And again, we're assuming that essentially all of the silver is in the form of this diamine silver complex. Okay, so the silver amine complex, we call that X. Chloride is X. And ammonia is 3 minus 2x, the quantity squared. Okay, since we're using up 2 equivalents of ammonia. Okay, if we take the square root of both sides and rearrange, we get X is equal to 0.15 molar. Okay, so the molar solubility of silver chloride in 3 molar ammonia is 0.15. And so we can see that if we add ammonia, the silver chloride becomes much more soluble. Okay, the next problem involves deciding whether a precipitate will form when solutions are mixed. Okay, so we have 0.150 liters of 0.1 molar lead nitrate and 0.100 liters of 0.2 molar sodium chloride. Okay, so cations and anions will exchange partners here. We'll get lead chloride, lead 2 chloride, PbCl2, and sodium nitrate, NaNO3. Okay, sodium nitrate will be soluble, but lead 2 chloride will precipitate if our Q exceeds our KSP. Okay, so what we want to do is we want to calculate the moles of each. Okay, so we have 0.150 liters times 0.1 moles per liter. Liters divide out. And so we end up with this many moles. Then we have moles of chloride. We calculate that the same way. So PbCl2 is the salt we're looking at. And then we need to calculate concentration. Okay, so we just calculated the moles, then we need to calculate moles per liter. Since we combined the solutions, it would be the total volume. Okay, so this is 6 times 10 to the minus second. Chloride is 8 times 10 to the minus second. Okay, so this is our IP expression. IP is, again, the same thing as Q. Okay, so we'd substitute this value in for lead. We would substitute this value in for our chloride. Don't forget to square it. And that is 3.8 times 10 to the minus fourth. Okay. Since the KSP is 1.2 times 10 to the minus fifth, okay, our IP is greater than KSP, so the answer is yes, lead 2 chloride will precipitate.